Started. We just finished talking about SIFT. Am I right? Yep. Okay. So you have the paper in Canvas for SIFT, which it's just a way of finding invariant scale, some sort of a fine invariant transformation, I could say. Features in the image. So we have seen two mechanisms, right, to do low-level vision. The first one is to extract just some basic edge detection, right, some edges from the image. And the second one is to extract points of interest, such as unions at different scales. And in particular, we have put quite a bit of emphasis on SIFT, which is an efficient algorithm to extract these points of interest. And then we're going to be using these algorithms all the time throughout the course to detect points of interest from images, to do image matching, to do reconstruction of scenes and objects, etc. Okay? All right. There is an extension of SIFT that's very popular because it's very efficient. And it uses a technique, a method called the integral image, which was very popular in computer graphics before being applied to computer vision. So let's briefly discuss this. Okay, so what happens is in linear filters in general, just not for SIFT or for edge detection, but in general, every time that we want to do a sum of pixels, meaning a convolution, right? For example, every time that we do a convolution, that is going to be computationally expensive for us, right? I mean, obviously, we have Fourier that allows us to do that relatively fast, but this is still computationally expensive. If you want to develop algorithms that work really fast and are not very taxing in space and time, then you may want to use that solution that I'm going to describe here today. So what we're going to do is we're going to pre-compute a lot of our possible addition of pixels in the image. And to do that, what we're going to do is, okay, I'm going to say an image, or the sum rather, right? So I'm going to use the term sum here of a portion of the image from the point x, y. So I meaning that I'm going to add points that go from 0, 0, up to x on the x direction, right, and up to y on the other direction. So this is, we can write it, this is not complicated, as all the x primes that are smaller or equal than x, all the y primes that are smaller or equal than y, and then just sum the elements, right, of that image, the actual pixels in that window, right? So basically what I'm doing here is I select a small window here that goes from the 0, 0 position or pixel to the x, y pixel, and I'm summing over all the pixels in that window, right? Okay. So you can use that technique to compute as many sub-windows as you want. So for example, I could now compute this other window here, right, of pixels that goes all the way to, say, if I'm going to call this x1, y1, maybe this x2, y2 now to make it even clearer, right? So I can do these things over and over and over again for all the possible summation terms that I'm going to need later. Now, to compute the sum over a particular square window in the image, which is what we do in linear filters, isn't it? Right? Then that means that we have to, from an image, that's my image, I have to select some points A, B, C, and D. Let's say that this is my A, B, C, and D. Okay? So I want to compute the sum over that specific window, right? And the way I'm going to do that, I'm going to use a number of already computed windows that I have here. So let me probably start with definitions. Let A be given by xa, ya, right? B, the point B, it's going to be given by xb, yb. C, it's xc, yc. And finally, D, xd, yd. Okay? And now if I want to compute this, this type of equation, but now within this window, then that corresponds to, let's see, the sum of all the pixels, x primes, y primes, for which x and y are in the interval a, b, c, d, right? Or I could say, if you prefer, you can write it down as x has to be between, let's see, xa and xb, right? And y has to be between ya or yb, doesn't matter, and yc or d. Right? So now if I use this to compute this previous windows here, right? So I use this equation here to compute these windows that I have, right? So this big one defined by D, this smaller one defined by A, this one here defined by B, and so on. Let me call these IA, B, C, and D, right? And hence, this is going to be equal to, let's see, I'm going to have ID. I'm going to start with ID, right? It computes this big window right here. I'm going to subtract from this, say, I'm going to subtract this area here, right? So to subtract this area, I'm going to subtract IB. But because now I have subtracted this area too, right? I don't need to subtract IA. So I'm going to subtract IC. But now I have subtracted IA twice, right? So I'm going to have to add IA, right? Is that right? And that's it. That's a simple way, simple mechanism to compute this. So the reason I introduced this method now is because there is this method called SIFT, which is similar in essence to SIFT, but it uses this technique, this trick, to actually compute the results of linear filters with approximations of Gabor's or derivative of Gaussians, right? And what we're going to do, as we had done way back in 5460, is to define a kernel matrix, right, for the linear filter that approximates what a derivative of a Gaussian or a Gabor filter is going to look like. And specifically, things that are typically done, let's see, or kernels rather, they're typically used are things like this. Let's see, I'm going to do. So, okay. So if I have a kernel like this, I'm going to select maybe this pixels here and these pixels here to be represented by +1, and then the center pixels to represent -1. So this one's here to represent -1, and everything else is going to be 0, right? And sometimes you'll see people maybe extending that -1 to this window right here, and these two windows right here, and this windows right here, right? And what does this approximate? Anyone? Anyone can tell me what this approximates? It approximates the second No one? We actually did this in 5460, so you may want to go back and review those lectures, right? This approximates a second derivative of the Gaussian, right? Okay, so where you have in 2D, right? In 1D, remember that it's called a Mexican hat because it looks something like this, which is nothing like a Mexican hat. So it has this three-dimensional, right, Gaussian like this, and then it has these valleys, right, also in 3D, obviously, right? There are negative, right? So these are negative, and this is positive. So this is positive, and this here is going to be negative, or vice versa, and this looks something like this, right? Or vice versa, as we have done here. And then another one that people use would look something like this. These are a +1, and these are -1. And what does this approximate? Anyone? That approximates another derivative of the Gaussian, right? That looks something like this, right? Have these two negatives here and this positives here, right? Should be symmetric. Yep. Okay. So as we had done before, these are just approximations of the Gaussian filter. You can assume they are zero mean if you want, with some variance or some covariance matrix if that's multidimensional, multimodal, excuse me. Okay. And in particular, these kernels here, right, that we use as linear filters, these are called Harr filters because they are discrete descriptions of very famous wavelets, okay, that I have mentioned. Although we have not covered that topic, we have mentioned that. So we can now use this integral image approach to quickly compute the convolutions of these discrete filters on the image and obtain image points of interest that we have also called, remember, fiducial points, right? And we're going to be referring to them as fiducial points all the time when we extract fiducial points, meaning points of interest, from the image that we then use for solving computer vision problems. Okay, any questions? So you also have the SIRF paper in Canvas. Okay, so make sure to review SIFT and SIRF because these are important papers that you'll be using later on in the course to solve several of the projects that we're going to assign. Speaking of which, as I mentioned the last time, there is the first homework, first project already available in Carmen. So make sure that you download this, you review it, and that you submit it as soon as possible. It's a very easy project, but it requires some time for you to get started with this. And make sure that you do this as well as possible because the second project is a much more challenging project than this, and it builds on top of that first one. So make sure that you have done this quickly so that when the second project comes in the middle of next week, you're ready to tackle that challenge. Now for this first project, you have to implement it yourself. You cannot use software that's available out there and implement it in MATLAB. It's easy enough, but you have to learn how to use these equations that we have given here in class, how to visualize the result of the Gavors and so on. Okay? All right, there's a question.
Where you have the red blocks on the first kernel, should the red blocks be the same?
Yeah. Like the same sign. So either.
Oh my gosh. Yes, positive. Positive. Yes, thank you. Yes. My bad. Thanks. Any other questions, comments, typos? Okay, so this is then the second hypothesis with regard to what low-level vision really does, right? So let's review. Thus far, we have the hypothesis that the early visual cortex detects edges of images, and those are points of interest. And I mean, let's face it, right? Edges tend to be points of interest because those are the points where those are the points that are going to define the edges of objects, the edges of different components of a scene, et cetera, right? So in between, if there is a constant color, there's probably going to be very little of interest to us, right? So, I mean, it's not such a terrible idea that that's what the visual system does, and that's in fact what Hubble and Wiesel's work seem to suggest, right? But then later on, people are studying these early cells in the visual pathway, in the ventral visual pathway, discovered that they responded or they acted like Gabor filters or wavelets. So there is this hypothesis that maybe that is what early visual cortex does. And then we discovered that if you actually use these Gabor filters or this derivative of Gaussian filters as a linear or as a kernel in a linear filter, then what do you obtain? Well, you obtain edges, but you can also obtain other types of points of interest, such as unions, right? The question becomes then, okay, if I can extract all these edges, all these unions, what is the scale that I need to use this into? And the solution is, well, all of them, right? So you do a space scale model, and then that allows you to look into different scales when you have to match different images or analyze things at different scales, right? And then from here, we derived several simple algorithms like a corner detector. And from that, we showed how to derive more interesting algorithms such as SIFT and SIRF. Okay? All right. Now, later on, a new hypothesis came up. And the reason new hypothesis came up is because there is an actual interesting or interesting and strange fact about how the early visual cortex in humans work, and that is that you go from a lot of information, meaning that you have a lot of cells. Remember from 5460 that we have cones and rods in our retina. So you have a lot of those, probably about 100 million, right? So you have a high resolution image in the back of the retina, but that these have to be compressed significantly by a huge margin in order to go through the optical nerve, right? So you reduce this to just a few million cells, whose accents are actually transported to the LGN and then to V1 in the back of our heads, right? But then after that, in the LGN and in V1 and V2, there's an explosion of representation. There actually is a huge overrepresentation compared to the amount of information that reaches those regions, right? So are these filters that, or these responses, like Gabor responses that we were considering, actually useful to detect edges, or just a side effect, if you will, of trying to extract useful information from the image to compute or to solve mid-level and high-level problems in vision, right? So that's the question. And the hypothesis is that you may actually want to extract as many statistics from the image as possible in order to find causal factors that have generated that image, right? So you have an image, and there are some causal features in the world that have caused, right? That have been the cause of that image that has been generated in the back of your retina. So is the brain, in fact, trying to identify these causal relationships, or these causal features, excuse me. So before we can get into, before we can dabble into this question in detail, I'm going to review one major method of analysis that we use in computer vision that we spend 2/3 of 5460 talking about, linear least squares, right? And then we'll talk also about its nonlinear extension and so on later on in the course. But this is such a fundamental tool that I want to review it. Now, if you want a more extensive overview of linear least squares, you have to take 5460 if you haven't taken it, or watch the videos. And if you want another more advanced review of least squares, then my machine learning course covers that in more detail. I'm just going to give here an overview, because this here for us is just a tool that we're going to use that I assume you already know. It just needs to be reviewed. Okay? Obviously, that's the fundamental tool that we are going to be using. Okay, so let's review linear least squares. And to review this, what I'm going to do, I'm going to start talking about correlations to begin with. So let me give you a very brief description. So I'm going to make a huge parenthesis, which is going to last probably the rest of the lecture today, right? So that in the next lecture we can pick up from the point where I left it now, okay? So that doesn't mean that if you already know least squares, you can just shut down and come back next week. I suggest that you still listen, because there's always something to learn about what we're going to discuss. So again, this is linear least squares. Right. I usually write it as least squares. Whenever we say least squares, we mean linear least squares, unless I specify it's nonlinear least squares, right? Which is possible, and we'll talk about this. Or it is obvious that I'm talking about nonlinear least squares. Okay. So when we study problems when we will study problems in mid-level vision, and especially in high-level vision, we'll be talking about feature spaces, right? Now, a feature space is nothing else than some space, maybe in the real domain of p dimensions. We will also work in the complex domain of p dimensions. Once in a while, we'll work on the surface of a hypersphere of p dimensions, so sp minus 1, right? So the surface of a hypersphere is, for example, the circle S1, right, in 2D, the sphere in 3D, which would be if you have a soccer or a basketball. You just take the thinness, right, the differential of the surface, right, and that would be S2, and so on, right, S3, S4, S5. Not to be confused with the ball of p dimensions, right, which is the actual ball filled in with all the points within the ball corresponding to that convex object, right? The surface of a hypersphere obviously is non-convex. So we're going to work with these feature spaces. And these feature spaces, most importantly, are given by some basis vectors here, right? And we're going to call them, for example, E1, E2, E3, right? And so on, all the way to EP, right? So E1 through EP are going to be my basis vectors that define that space. Now, you might remember from 5460 when we defined the Euclidean space, right? In the Euclidean space, these are orthonormal vectors, right? Their length is 1. The norm of each vector is 1. They are orthogonal to one another, meaning that if I do an inner product of two of them, that's equal to 0, and so on, right? You remember from 5460 as well that in an affine space, the norm of these basis vectors does not need to be 1. It can be any number different than 0, and that their inner product does not need to be 90 degrees, right? The angle between them doesn't need to be 90 degrees, and therefore their inner product doesn't need to be 0, right? And so on. When we talk about projective space, we'll talk about other properties for those types of spaces. Now, why am I so interested about feature spaces? The reason is because, remember, our theory says that we want to go from low-level vision to mid-level to high-level. Now, for simplicity, let's assume that high-level is object recognition. It could be anything in high-level. We'll talk about all the things that it could mean, but let's assume it's object recognition, right? So here we extract some features from the image. For example, as we have said, edges, unions, SIFT features, right? Other things that we're going to define, maybe the response to some of these Gabor filters or wavelets, right? And then each of these features that we extract in low-level vision are going to be used to define the feature space. That's where we're going to represent our image, right? And once we have the image represented in that feature space, we're going to analyze it in mid-level and high-level vision to extract information from it. But before we can do that, there has to be a space, right, where we can do these computations. That's why we're interested in low-level vision. Low-level vision is interested in what are the features that I need to extract from the image in order to find a convenient representation that I can then use to solve other vision problems. So far, so good? Excellent. OK. So first, what are the features, right? That's something we'll need to solve. Features can be, as I said, edges. It can be corners. It can be other unions. It can be SIFT features. Second, is that going to be in the real domain? Are it going to be orthonormal vectors or orthogonal vectors? Is that defining an affine space? Is that in the complex domain, right? And we'll work with all of these. OK. Now, for example, another type of features that we'll be working with is if you start with an image, actually, let me give you a couple of examples. If we start with an image, maybe that image has an object, right, right here. And that object has a shape, and that's the shape. I don't know what that shape is, so just some shape of some object. And from it, we have extract some of these fiducial points of interest, right? Then what we may be interested in for mid-level vision is to find a feature representation here, feature space, that represents the shape of that object, right? One way that we will do that, for example, is we can find the center point, the center of mass, for example, of all these fiducial points that we have extracted, compute the distance to all these fiducial points. And then each of these distances, let's call it D1, D2, D3, and so on, all the way to the last one, dP, are going to define my vector, right? Let's call my vector x with the values D1 to dP. So far, so good. There are many other representations for shape that we talk about, right? That's just one possible way of representing the shape of an object. And our concern in mid-level vision and then in high-level vision will be, OK, what type of representations should I implement such that they are invariant to scale, to rotation, to translation, to affine transformations, and so on, right? So we'll talk a lot about this. Another approach, this, by the way, has a very difficult name to remember, this approach that we'll talk about later. You don't need to write this down now. This is called shape-based approach, right? Very convenient. So easy enough, right? OK. Another one, what we're going to do, another approach, is we're just going to take the pixels of our image, right? So we have our object somewhere here in the image. Right? And what we're going to do, x, it's just going to be the intensity value, right, the brightness of each of the pixels. So we're going to look, say, the first pixel is going to be the top left corner right here. And this, we're going to use it as our first entry, x1. OK? Our second pixel here is going to be our second entry of the vector, x2. This one is going to be x3, and so on. Once we finish the first row, we're going to go to the second row, then the third row. And it doesn't matter whether you then start back to the left, or you go from right to left, and then left to right. And it does, or if you want to read it in columns rather than rows, as long as you always follow the same pattern, it's up to you, OK? And if you have p pixels, you're still going to end up with a vector like this. And in all these cases, we're going to assume that I'm in the real space of p dimensions. Now, this is true for shape. If I compute shapes that way, we'll actually define them more conveniently in the complex domain. We'll see that. But if I just compute the distances, then these are just real numbers. This is a little odd because pixels, the intensity of a pixel is not a real number. It's an integer, right? You can, if you have 8 bits to define each pixel, it's a number between 0 and 255. So, but let's assume that they were real numbers, right, for simplicity. And I have a lot to say about all these things in machine learning, but I'm not going to spend time here. But you do have the lectures online if you are curious and you want to learn more about this. OK? So far, so good. Are these two approaches clear? Now, the second approach, by the way, is called, generally, you'll see it called the appearance-based approach. OK. So far, so good? Yeah? Is that clear? All right. So what I'm doing here, right, is generating vectors. So I'm going to have vector xi here. Let's say going. All right, there we go. xi, right? So that for each image that I have, I'm going to obtain a vector xi, right? If I'm defining this in the space, my space is the real space, the real domain, excuse me, of p dimensions, then what's going to happen is the first image is going to be represented as a vector in that feature space of p dimensions, right? My second image is going to represent it like another vector in that space, right? My third image is going to be represented like another space, another vector in that space, and so on, right? All the images that I have are going to be represented as vectors in that feature space. Now, a first thing that I'm interested in is to determine whether these features, so are the features of my feature space correlated. Let's see what that means. Correlation means that if I know the value of a feature here, I automatically know the value of the other features. Okay? Now, if we talk about linear correlation, then what that means is that there's a linear function that converts the value of the first feature into the value of the second feature, right? So let's write this down, because this is very important. So what that means is that my feature, so if I have a vector, say x, right? This is my vector x equals x1, x2, right? Then it's going to mean that, for example, x2 is equal to a linear function f of x1, right? So maybe, I don't know, just maybe, right, as an example, e.g., x2 is equal to 2x1, right? In which case, if this is my first basis vector e1 and this is my second one e2, then I'm going to have a line that looks like this, right? For each value of x1 here, I'm going to have 2x1, right? So 1 is going to be 1, 2 is going to be 4, and so on, right? 3 is going to be 6, etc., right? Yep. So linearly correlated means that there exists this linear function. Now, we'll see more about why this is interesting, but let me give you a glimpse to some of the important points why this is interesting to us. So for example, here in the appearance-based model, okay? Now, if I consider pixels, different pixels, neighboring pixels of the object, right, that these 2 pixels correspond to different dimensions of my space, right? But some of these neighboring pixels are going to be basically of the same intensity. So imagine that the object is a face, right? If I take the pixel of that position in my cheek or the next one on my cheek as well, they are probably just going to be identical. And if not identical, almost identical, right? So if I already know the value of that pixel, I don't need to know the value of the other pixel. That's absurd, right? So that's why I'm interested in this. Because for one, this is going to allow me to determine which of these features in my feature space are relevant and which are not. Because I hate to keep information that is too redundant, right? Now, in the appearance space model, if I have an image of p dimensions, imagine that you use a very simple low-resolution camera these days that only takes 1 million pixels, right? Pictures. Then you have 1 million dimensions. Now, what can you represent in that feature space of 1 million dimensions? That the space can represent all the pictures you can ever take of every object under every possible pose, scale, illumination, etc. Right? Now, if you're only interested in images of chairs, do you need the whole space? No, you're going to need a portion of that space. But we don't know what portion of that space, right? But chairs, more likely, if I just take pictures of chairs, chairs are going to give me a lot of correlations here because chairs have a specific pixel correlations. And that's what I'm looking for, right? Which ones? That's going to allow me to find a very compact representation for chairs. Also, when we get to high-level vision, right, that automatically gives us a method to do recognition of objects because the correlations of these features for a chair are going to be different than the correlations of these pixels for tables. That just gave me an idea. I can use the fact that the correlation of the features for chairs and tables are different to determine whether I'm looking at an image of a chair or an image of a table, right? So correlation is going to be useful for a very large number of things. So we're interested in finding these correlations, in defining these correlations. So let's see how we can do that. OK, so if we have our vectors xi's in p dimensions, right? Vectors in p-dimensional space, real domain, then I could say, maybe let's start. I'm going to generalize this very quickly. Let's start with p equal to 2 for simplicity. So then I have xi1, it's equal to negative b over a times xi2 plus d over a, right? I can have this relationship, which I could also write, obviously. This is the same as a xi1 plus b xi2 minus d equals 0, right? These two equations are one and the same, right? And this equation right here is the equation of a line, right? This is the simplest linear relationship, right? OK. Now, if xi1, or all xi1s and all xi2s are correlated, right? Meaning that there is that linear function f, this equation of a line, that given xi1 or even xi2, in that case, I can compute xi1, right? Then this equation will hold for all xi's, right? Let me write it this other way. So I'm going to add over. So this is the sum from I1 through n, and the number of simples that I have, or vectors here, right? So these are my simple set, capital X, I'm going to call it x1 through xn, which I will generally write like this, from 1 to n, a set of x1 through xn, okay, of elements. And each xi, remember, can correspond to an image, to a shape, to whatever we're going to come up with later. So if I sum over this, of this equation, axi1 plus bxi2 minus d, right? If I do this, and and the first dimension in the feature space and the second dimension in the feature space are correlated, what will this be equal to? Go ahead. What? 0, right? Because each of them is going to be 0, so the sum is going to be 0. Let's call these, okay, let me square this. It's still going to be 0, right? 0 squared, last time I checked, it's still 0. So let's call this R, okay? You call this R. Now, R is going to be 0 if they are correlated, the two dimensions. What happens if they are not correlated? Let's see. Let's see what's going to happen when they are not correlated. Now, let's draw this here. If I have totally correlated vectors like this, right, so that there's a linear function between them, they're going to look something like this. There's a clear function, right, this line that defines a projection of one to the other. So I'm done. So this R is going to be 0. What's going to happen if I have vectors like this? What's going to happen in that case? What's R going to look like? Okay, let's think about another problem. Let's think about this problem here. What happens if I have this? What's going to happen in that last case? What's R going to be? Right? Because there is absolutely no correlation, right? For if I know the value of the first feature, right, say the horizontal feature, that doesn't tell me anything about what the value of the second feature is going to be. It can be any value, right? So there's no correlation, right? So here, this is correlated, and this is uncorrelated. And this is going to be somewhere in between, right? So here I can minimize that value of R, making it 0, right? Because there is a function f that converts this value here into a perfect value there, a unique value. Here, that R is going to be very large, right? Because there is no hope in predicting what the other value is going to be. And here, right, for any value of xi1, I'm going to have a range of values of xi2 for that I'm going to be in, right? It cannot be any value, but I know it's going to be in some range of values, small range of values. So R is going to be somewhere in between these two extremes, right? Okay. And if we do this for, in general, more generally, then, right, for any p, so for any p instead of just 2, then our equation is going to be the same, only that you have a1 xi1 plus all the way, whoops, I forgot the summation term, right? The summation from 1 through n, all the way to ap xip, right, equals c, so minus d, right? And I'm going to square this. Now, I could square or take the absolute value here. It doesn't matter. We generally square this because, as we're going to do now, we're going to take the derivative of this. It's easier to solve for the square than it is to solve for the absolute value, right? Because the absolute value doesn't have a derivative at one specific point, right? Because although it's continuous, it has that peak, right? That's easily solvable. People always say, oh my gosh, we use the square because the other one is non-differentiable. Well, it's just at one point. This is something we can computationally solve. Actually, it's really easy to solve. But it's just more convenient to use the square. Okay. All right. So let's see how we can derive now an algorithm to find these correlations, to determine which features are correlated and which features are not correlated. Okay? So far, so good? Okay. So let's write this equation that we have here, this final equation that we have come up with here, right? Let's write it in separate equations for each of the images or samples that we're going to have. So I'm going to get a1 xi1, or actually I equal to 1, so the first image, so 1, 1, all the way to a p x 1p minus d, right, equals 0. Or actually, why don't I just say equals d? That's actually easier. Same thing. If you want to write minus equals 0, it's fine. Then we're going to have a1 x21 plus ap x2p equals d, all the way to the last sample. How many samples did I say, or images that I have? N, right? So xn1 plus ap xnp equals d, right? And that's a system of linear equations, right? All right. If I have the same number of, so let's assume that they're linearly independent equations, okay? For simplicity. They don't have to be, but let's assume that they are. If they're not linearly independent, you can just get rid of the ones that are not linearly independent and just leave the ones that are linearly independent, okay? So let's assume that the ones I have here are already linearly independent. If I have less equations than unknowns, right? My unknowns are all the a's. The x's I know, right? The a's and d are unknown to me, right? So if I have less equations than unknowns, how many solutions do I have? Anyone? Infinite. Very good, right? Obviously. If I have, say, A, B, and C are my unknowns, right? And I have these two equations, 2a plus b equals 3, and b plus 4c equals 1. Where are the values of a, b, and c? There's an infinite number of solutions, right? Obviously, because I don't have enough equations. Now, if I had the third equation here, meaning I have the same number of equations than unknowns, how many solutions do I have? right? Very good. 1, obviously. Again, assuming they're linearly dependent. Okay. So if I have less samples or less images than unknowns, there's nothing I can do. I'm lost. There's no hope. If I have the same number of equations and unknowns, then I can find the one solution, right? But if I have the same number of equations, means the same number of images than unknowns, I can always add a new image, right? Easy enough. And then at that point, if I have more images or samples than unknowns, then how many solutions do I have? So let's see. Let's say A is my sole unknown, right? Just have one unknown. And I have 2 equations. How many solutions do I have? What was that? No solution, right? I'm just symbolic. How are we going to solve this? It's ridiculous. There's no solution. So, no solution. Okay. So I either have infinite solutions, which doesn't get me anywhere. I have one solution that I can easily convert into no solution, which means that I don't have a solution. Right? So in general, we're going to say there is no solution to this problem, because we are always going to make n larger than p. Right? So what we want to do then is instead minimize r, that value here, right? That we can do. We know that if this r were 0, then I would have just one solution, a unique solution, right? So if it is possible, then that's the ideal solution. If not, I want r to be as small as possible, right? So I can get as close to an actual solution as I can get. Okay. So let's rewrite this. So for the time being, let's assume that d is equal to 0, and I'll come back to d not equal to 0. Okay? So assume for the time being that d is equal to 0. And I'm going to write capital X as the matrix whose rows are the xi's. So I have x1 transpose, x2 transpose, all the way to xn transpose. And I'm going to have a vector A which has all the unknowns, A1 through AP. Okay? And that means that I can rewrite this equation right here, this equation, the set of equations that I have, as capital X A equals a vector of zeros, right? Right? It's the same thing. You agree? Okay. So what I want to do is minimize R, this R that I have written here, right? Which is this equation's squared, right? So I want to minimize R. Now R is X, capital X A square, right? Yes? Which I can write as, you'll remember from 5460 or just linear algebra, I can write this as A transpose capital X transpose XA. So far, so good? Yes? That's a square. In fact, I can call this matrix Q, right? Q is nothing else, capital Q is nothing else than X capital transpose X capital, right? Or capital X, right? Okay, so what I want is to minimize A, Q, A. That's my goal. Okay. That seems easy enough. Very doable. Now, a few properties about Q Q is a symmetric matrix, is it not? What do you think? It has to be symmetric, right? It's X transpose X. By definition, it's symmetric. Remember, symmetric means that Q and Q transpose are exactly the same. But it has another property, important property, is positive defined, right? Or semi-defined, because it could be 0, presumably, right? But it's either all the entries in Q are either 0 or positive, because it's X transpose X. It's just no way you can end up with a negative number. Well, that's what this square does, right? This square right here guarantees there are no negative numbers, right? So this is a positive semi-definite matrix as well. So I know that A transpose QA is going to be equal to some scalar, right? Some real number lambda. And I want this lambda to be as small as possible, don't I? So I want to find the vector A such as when I project the matrix Q onto it, right? By doing this multiplication, matrix multiplication, I get the smallest possible lambda, right? And we have, because this is a symmetric positive semi-definite matrix, we have a tool in our statistic arsenal, right? Or linear algebra, rather, arsenal, that we can use, which is we can do an eigenvalue decomposition of Q, right? And if I do an eigenvalue decomposition, I'm going to get many eigenvectors, right? These eigenvectors are possible solutions to that system of equations, in fact, right? All the possible A's. And the corresponding eigenvalues are these lambdas, right? And which eigenvector do I want to take? The one associated to the smallest eigenvalue, right? Because that's the smallest error. Remember, this is equal to R, right? So lambda is R. I want to minimize R, so I want to take the smallest possible eigenvalue. And that eigenvector is going to give me that solution for A. That's simple, right? It's extraordinary. So in general, we're going to say if A is the set of possible solutions, right? This say P, right? So A, it's a matrix whose columns now are all the possible solutions, all the possible eigenvectors. And capital lambda, it's going to be a diagonal matrix of the corresponding eigenvalues. Whoops. P. Right? And you have to choose some orientation for the eigenvalues, right? Meaning from largest to smallest or smallest to largest. Doesn't matter to me whether you say lambda 1 is the largest and lambda p is the smallest, right? Or lambda p is the largest and lambda 1 is the smallest. We have to choose one of these orderings. And then with that, you just decide that A, your solution here, right? The solution for A is going to be, if this is the ordering, it's going to be my AP from here, right? This eigenvector. Now, also note that obviously I could keep all the eigenvectors, right? Capital A transpose Q, capital A equals capital lambda, right? This is just a generalization of this, right? Given the eigenvectors and the eigenvalues. And because you know that A transpose A, obviously it's equal to the identity matrix, I can also write this as QA equals A lambda, right? which is the eigenvalue decomposition that we are using, right? Right? Okay. All right. So what I can do is I can use the first solution I can use the first solution, AP, to determine what the smallest possible error that I can have is, right? That lambda p, and then assign this as my solution, AP, right? I can also take AP minus 1, which is the second best possible solution, right? And that's going to give me two possible solutions, right? They're in fact orthogonal to one another because eigenvectors are orthogonal to one another, right? By definition. I can take the third one, AP minus 2, and also take it as a possible solution, etc., right? And we'll see how to do that, how to use that. Okay. I don't have time to probably cover the next step. So I'm going to do this next week. Please review this because this is fundamental for everything else that we're going to do next week. And make sure that you work on your project because that's also going to be extremely important for everything else that we're going to do next week, which is going to be very exciting topics in low-level vision. I'll see you then.